I would like to present the winner of the Pulmonary Embolism Detection Challenge hosted on Kaggle this year from RSNA and STR. It's the third running of competitions on CT scans, and this is the fifth place solution. A little bit about myself. I'm an AI engineer working at Doubleyard, which is focused on the ed tech space and specifically on computer vision in that area. I also lecture at the Berkeley Masters of Data Science program. I'm going to talk about the components of the solution: windowing, cropping and augmentation, image classification, the extraction of image features, and then how those image features were sequentially modeled. The hardware used was Linux with A100 DGX stations, and a big big shout out to Doubleyard for their support in providing that compute. This was really nice. It's the latest cards out from NVIDIA and much faster than anything else you can find in the market. You can see some of the softwares there. So again, thanks to PyTorch and our white man for his work with the PyTorch image models. It made it very easy to work with. The windowing approach was done by going through each of the CT scans and windowing over to the lung, PE and mediastinal window. Each of these were mapped to a certain channel within a JPEG image, which was saved to disk. And the credits here really go out to Ian Pan. I put up a link to his solution. I'm not sure if you can click on the link, but you can definitely go to the discussion forum and check out what he said there. The augmentation was pretty light. There was cropping, and actually there wasn't cropping, there was vertical flip and shift, scale, rotate. So part of the reason we didn't do a lot of augmentation was because some of the target labels were left versus right if the condition was on the left or the right of the scan. For feature extraction, we made an image classification model. This was using efficient nets, which I thought would be a good balance of accuracy and low memory on the GPU, because the submission process was constrained on compute. So I wanted to keep it to lighter models. In retrospect, that might not have been the best decision, but yeah, that's what I went with. And the loss here was pretty important. So what we did is, for images, we took the loss of every image and averaged that over the batch. But for a study, so things like the severity of the condition and whether it's on the right or the left side, etc., we only used the loss on positive images, so masked it so that we ignored the loss on negative images and then took the mean of the loss on positive images. And also, what's not mentioned here is I oversampled at a rate of 4:1 negative to positive images, because there is a heavy class imbalance within the dataset. And every epoch had at least 2 images from every study in the dataset from the 7,000 studies. After training the image classifier, we took out the image features from that. That was through the gap layer extraction. You can see here the gap layer, which is the final layer that's typically used prior to classification. And we sequenced that up according to the images that were seen within the study scan. And you can see here an example of why it makes sense to do this. If you take you have image classification, and I showed an example where we have study labels. So for example, negative and this would have the severity of the overall scan and whether the condition is on the right or the left side. And typically that's bunched together because the scan moves across from right to left or whatever. So it'll start seeing the same thing in a sequence of scans and then move off to the end where it doesn't see the condition anymore. So it's pretty useful to sequence up the features from all the images. This was passed through into two different types of models. One was a bi-LSTM, which was pretty similar to what was done last year. The second we added on to last year's solution was transformers, where it had a single layer with 2048 hidden and a double layer with 1024 hidden, and basically averaged all of these. The loss function used here was a change on last year, and we tried to get as close as we could to the original loss, the competition metric that the loss function would be measured on that. Obviously each sample here that was passed in was a whole sequence, so a single study, a whole sequence of images. So finally, we split the data into 5 folds, and 3 of the folds were used. You can see how the fold is done. It's with the out of samples, and for every fold we got efficient net and those 3 models, and then in the end averaged the results of all the folds and all the sequential models. You can see here the link to the GitHub and also the submission, because the GitHub just runs up until we have the weights for all the models, and then they're used to make a submission within the Kaggle script, which is linked here. And also you can see the competition, and there's right up to my solution. It's actually linked within the GitHub. So if you check out the GitHub, you can see some technical details, but also a write up to the competition, to the approach in the competition. So again, thank you, and I'd like to shout out to the RSNA team for putting together this excellent data set, and all the work that went in there from all the teams who annotated this data, and very much looking forward to next year to see which challenge is put to the community next year. I hope to see you back. Thank you.